Okay, so this session is going to be on PSF photometry. And we're going to go beyond the aperture photometry that you saw in the beginning. And when you think about aperture photometry, we know that, like, intuitively it makes sense that to measure the amount of light from a star, we just want to sort of add up all the photons that we attribute to that star and say, well, that's proportional to how bright the object is. And that, like, totally works. So it's, our physical intuition is sort of leading us in the right direction there. But there's a few caveats. And one is that we should really understand what the statistical reason that works is. And that basis, that statistical basis should really explain to us how to make the best measurement and not just sort of a thing that kind of seems to work okay. And the other thing is that we kind of know that aperture photometry can't be optimal because it has this sort of arbitrary radius parameter. And you know that if you make the radius too small, then you're sort of throwing away information because you're not counting the extended PSF of the star. You're sort of losing that information. But if you try and capture that by making your radius very large, then you're starting to include a whole bunch of noise, which also doesn't seem optimal. So there must be something that's more precise than this. So we can try to make a maximum likelihood estimate. Because we have a model for what we think the light distribution should be in the pixels that we see, we understand the noise properties, and it can say what's the best estimator for the value of that flux that makes the model match the pixels we observe. So I'm going to go through a little bit of math, basically following the notation of this paper here, Portillo, Spiegel, and Finkbinder, just because I think the paper is really interesting for a lot of other reasons, and they deal with some of the detailed biases in photometry in general. There's a sort of classic reference to an Ivan King paper from 1983, where he also works out all the math of PSF photometry. So we're going to say that our PSF is this P of XY function, and for our model for a given star is just going to be to multiply that by a flux. That's assuming that the PSF is normalized, the sum of all those pixels is 1, and we're just going to assume that all the images are background subtracted. You can't really do photometry in the same way on an image if there's a big background behind it. So because the noise on the pixels is uncorrelated, that means that we can compute the likelihood for each individual pixel and then just take the product to get the measurement for the entire set of pixels that we think the object is sitting on. So we'll make f hat be the measured flux. Don't think of the hat as being an estimator. Think of that as a noisy realization of the flux. And then we assume Gaussian noise, and I can write down the likelihood function as just the Gaussian function of the difference between the measured flux and our model flux for a given value of f. Taking the log of that turns this into a sum, where now we're just summing over the differences between the model and the realized data. And because we want to find the place where this likelihood function is maximized for a given f, we want to find the f, the flux of the star for which this likelihood function is maximized. We're just going to say that the partial derivative of that with respect to f is going to be 0, and we're going to find this flux sub ml, that's the maximum likelihood flux for the star. That gives you these two terms. You sort of pull the PSF over into summation. You pull the maximum likelihood flux over on its own, and then you get the ratio of these two summations, where the we're essentially taking the product of the PSF model times the flux in each star corresponding to that that PSF model pixel. And then we're dividing this by what's essentially sort of a normalizing factor, because it's not really it doesn't depend on the data. So in practice, that ends up being very simple to perform, because it's just a matter of making a realization of your PSF on the same place, like the same grid of pixels as your source, and then just multiplying these two together and taking that sum and dividing by the normalization. To sort of, again, confirm our intuition that things all sort of hang together here, we can think of this as being essentially a weighting scheme, where we're just going to sort of decide, well, how do we want to weight the pixels that are in the center of the star versus the pixels, the outer regions, and we can actually make this behave like aperture photometry, because if we just say that our PSF is like a top hat function, where the value of the PSF is just 1 over the number of pixels in my aperture, if I plug that into the PSF photometry equation, what I end up with is just a sum over the measured pixel values inside of that aperture, which is just aperture photometry again. So again, that's sort of confirming that our intuition that aperture photometry makes sense. It's doing a thing that's right, but actually using the correct PSF to weight the contribution of the different pixels is sort of the real optimal thing. So I kind of jumped directly into like, how do I do the PSF measurement? Sorry, do the measurement of the flux of the star. But that skipped the whole series of steps that get us to the place of being able to do PSF photometry. And so we need to know where are we even going to do PSF photometry. Like if I just hand you an image, you can pick out a star by hand, but how is a pipeline going to find all the stars and put down the PSFs in the right place to get those flux measurements? And so that's a few steps. One is the match filtering that I believe was discussed in one of the earlier lectures. We're going to convolve the image with the PSF. We're going to find places where that match filter says that there is some significant flux above the background level. Oh, sorry, I guess I should go to the next slide. Right, we're going to convolve the image with our guess of what the PSF is. But that just gives us like a list of all the pixels that are significantly above background. And we don't want to photometer like every single possible pixel. We want to end up with sort of a list of candidate positions for stars, where each one of those sort of entries on that list sort of corresponds to one star. And so we do this by essentially what we call peak finding, where we want to identify pixels in this convolved detection map where all of their neighbors have less flux. And this is sort of it's kind of obvious when somebody says it, but it's kind of a neat trick where it's basically saying that we don't want to do photometry on like the edges of of a star, but on the edge of a star, every pixel is going to have one neighbor which has got a little bit more flux in it than that pixel that we just looked at. And so we can find the pixel in the center where at least one pixel has to have more flux than all of its neighbors. And that's what we want. That's what we're going to call a peak. And that's our starting point. Peaks just tell us like just give us like a pixel that is a candidate for a star. But we can measure the position of a source more accurately than that, because we can use the whole information of that sort of distribution of light. And that will give us a centroid, which is much more precise than just plus or minus 1 pixel. So the next step in the process is essentially to turn these sort of integer peak locations into floating point, more precise positions to lay down that PSF. Centroiding is usually a sort of the algorithms are typically somewhat pragmatic, where they're trying to make an estimator which is robust, even though there might be all sorts of issues in the data of cosmic rays near your pixels or bad columns or something like that. And you don't, typically at this stage of the processing, you don't really know the PSF itself. So doing something like, you could write down a maximum likelihood estimate for the centroid. That depends on things like the derivative of the PSF, and we don't really trust the derivative of the PSF when we're still sort of in the first few iterations of processing the image. The Room Observatory uses a centroider that's borrowed from SDSS, where it essentially makes repeated quartic interpolations of the pixels, which lets it get around pixels which it thinks are bad, and finds where the peak of that interpolated flux distribution is. That's somewhat messy to think about, and it's not a thing that you want to just like implement on a whim. You can think of centroiding on a much simpler basis just by thinking of taking the mean of the pixel positions weighted by the flux in each of those positions. And that's a way to sort of just take the mean, using the mean position of the flux. It's sort of susceptible to outliers. So if I have like a cosmic ray on the edge, that might pull my weighted mean way far from the star. But for just getting your head around what centroid is doing, it's not a bad way to think of it. So once we have a centroid and we have some objects, when we have some objects and we have their centroids, we still haven't explained how we build this model for the PSF itself. That typically starts with identifying PSF candidates. So again, we kind of have to assume a PSF size in order to guess what objects, what sources in the image might be clean, isolated stars that would be good for measuring the PSF. And that's a kind of a bootstrap problem, where we need to have at least some guess before we can do that. And so we might run PSF determination and then come back later and determine new PSF candidates the second time once we have a better estimate of the PSF itself. There's all sorts of possibilities for looping in these algorithms. But we say we have some idea of what some isolated stars are in our image. There's a few different algorithms that can be used for actually modeling the PSF itself. The simplest is just to assume a functional form for the PSF, either one parameter or two parameters, and then to fit that in your favorite fitting algorithm. So fitting a Gaussian as your PSF is not a thing I would put into production at the Rubin Observatory, but it's not a terrible thing to just try initially. And there are fancier versions of this, like the Moffat function is designed to have the Gaussian core, but wings that are bright or reflecting what actual telescope optics tend to produce. But it's a sort of older style that's not used so much. In surveys like SDSS, what they did is they had a series of basis functions. So this would, the series of functions gives you a bunch of shapes, and you can fit the normalizations of those different shapes in order to capture both the shape of the PSF itself and to capture the variation in that shape across the sensors, because the telescope optics and the atmosphere tend to you don't get a nice, beautiful, constant PSF over such a large field of view like in a survey telescope. It tends to get sort of distorted around the edges, and so you want to be able to capture that in your PSF fitting. So by measuring these basis functions, you can have the values of the basis functions be functions of their position across the sensor. And the sort of most recent efforts at PSF modeling have used what's called a pixel basis, where we can think of this as replacing this set of basis functions, like SDSS, with a set of delta functions, each one corresponding to a single pixel, typically in a grid which has a little bit higher resolution than the actual images you're trying to fit. So you can use all of your PSF candidates to determine what's the values of this higher resolution pixel grid, but then those pixels themselves can also be functions of the position across the field of view again. So it's another way to capture this spatial variation, but it's extremely flexible. Because it's just this grid of pixels, the shape variation doesn't have to conform to your pre-selected set of basis functions. So I'm just going to sort of mostly wrap this up by describing a little bit of the plans for the future. And one of the big topics in modeling the PSF today is that we understand that there's both an atmospheric contribution to the point spread function and an instrumental contribution. And so a goal of some recent work is to separate these out and fit them in distinct forms, with distinct methods. So on the left, you see this is a map of the PSF shape residuals after removing sort of the basic structure across the CFHT field of view. And you see this sort of characteristic banding structure that covers the entire field of view that we believe to be caused by the atmosphere and the turbulence in the atmosphere as it passes over the observatory. But then there's also, on the right, this is a whole bunch of little models of the optical point spread function. Now this is caused by the telescope optics itself, and along with any positions and any position variations of the sensors that go into the camera. And so the variations in these PSFs from the optics, they're overall much smaller than the atmospheric PSF. So we designed the telescope optics such that the PSF is not significantly degraded by the fact that the optics have some PSF to them. But sort of importantly for a lot of cosmological work, these can contribute to the shape of the PSF in sort of subtle ways. And particularly in work like weak lensing, where you're trying to measure the shapes of galaxies, If your PSF has subtle correlations in the shape of the PSF across the focal plane, that can essentially cause either noise in your measurement, or even worse, it can cause sort of systematic biases in your measurement. So being able to apply a set of physically motivated models to the optical PSF, and then combine that with a different set of models that they're designed to capture the atmospheric variation, is hopefully a way to really tightly characterize the PSF in a way that's sort of necessary for doing the weak lensing science that LSST plans to do. So, just to recap where the photometry story, I've told you sort of the different components, but these are all sort of an iterative process, where you kind of have to make a PSF guess in order to do detection of objects, which then lets you do PSF determination. Once you've selected things you think look like PSFs, it goes maybe back into another round of detection, since you have a better estimate of the PSF, which goes into centroiding. And so this is certainly true in the room observatory pipeline, so we sort of loop through this process a few times. But the steps themselves are fairly straightforward, and you can just the noodle component should be fairly understandable, and you should be able to sort of do them one after the other and get sort of reasonable results without too much work. Which is what the notebook that goes along with this lecture will be covering. So that's the end of what I'm making the first part of this lecture, and then there'll be a second part, which is a separate file. Okay, so in the first half of the PSF photometry session, we saw how to measure the number of counts that we get for each star in our image. And that's useful information, but it's not the complete story, because we still need to transform that number of counts into something that's useful to compare to other surveys that's sort of on a more physical basis than just the number of photons that fell on my CCD on a particular telescope. So we need to obtain either magnitudes or physical fluxes in something like Jansky's, and that process falls under the category of photometric calibration. So we want to take our measurements off of this image and turn it into something that's scientifically useful to work with. So we're going to start at the very basic level of what it means to do calibration on these images. And the simplest way to think about it is that we want to report how bright the objects that we observed are relative to some agreed on standard, something that other people can compare to. In practice, this usually means, sort of today, that we're going to try and put our photometry, if it's optical photometry, on the same basis as like pan-stars or Gaia, because those cover large fractions of the sky and they're well calibrated for reasons which we'll talk about later in the talk. And so we can use that as our agreed on standard. Now, the advantage of calibrating to these big surveys is that it's likely that there are some calibration stars from either pan-stars or Gaia that are actually in the image that you took when we went to the telescope. Pan-stars doesn't cover the entire sky, but if you're somewhere in the northern 3/4 of the sky, it's pretty likely that there's some pan-star stars in your image. And because we can just go to the pan-stars database and ask how bright those stars are in magnitudes, that gives us something to calibrate to. And what we use is a sort of most basic calibration equation here, where This is basically just writing the magnitude equation down, where the magnitude is proportional to minus 2.5 times the log of the number of counts in the image, plus a constant, where that constant basically accounts for the fact that we need to scale the counts to magnitudes in some way that reflects, well, how big the telescope is, and how clean or dirty the mirror is, and how much light actually was collected by the CCD, and all that sort of messy throughput issues. But if we have some pan stars or stars or other calibration stars on our image, we know what their magnitude is, and we measured the number of counts in those stars, and so that gives us a way to solve for the 0 point for that image. And so that's the simplest way to calibrate our image, is once we've computed that 0 point, by taking all the calibration stars in our image and trying to minimize the scatter in that equation, that gives us a way to apply that same equation now to the stars that we don't know what magnitude they are, just by plugging back in that 0 point that we measured. Another way to think of the 0 point is that it's what magnitude a star would be if it only produced a single count in your image. And this works very well because CCDs are extremely linear. We mentioned earlier about how we correct for linearity. But that means that you can do relative photometry very robustly, because you're the only to first order, the only thing that's different between my CCD here and some other CCD on other telescopes is that the ratio of the counts that they collect might be a little bit different. So there's a few details that this leaves out. One is, how did Gaia or pan stars or eventually LSST magnitudes get to be good standards for calibrating images against? Like, what did those surveys do that made them that gave them robust photometry? Another topic that we'll get to afterwards is really like, is this simple 0 point the entire story? And what happens when we have surveys that are observing in different filters or observing on different telescopes, and what are the other nuances that we need to concern ourselves with in that situation? And one that I'm not really going to get to is absolute calibration. So at some point we need to define what the physical flux is of a 0th magnitude star, but that's in some ways it's a separate question than trying to put different surveys on the same basis in order to do comparisons between different surveys. So we're mostly not going to worry about that last question. So let's go into how these large surveys calibrate their data. And let's imagine that I'm running a large survey, but my large survey only has 2 fields. And in one of those, I have a calibration star, which somebody has told me is an 18th magnitude star. And so I can apply what we just discussed in order to calibrate all the stars in field A. But in field B, I was unfortunate and did not have any calibration stars that happened to fall into that field. And so I'm unable to calibrate that field. Let's just assume. So I can't really say what the magnitude of that star is, because who knows what the exact calibration level is without having something to compare it to. But if I get a little bit more data, if I get exposure C in the middle, now exposure C has some stars in common with exposure A and in common with exposure B. And so I can assert that, even though I don't have any calibration stars in this new field itself, I still have only this one calibrator. I know that the stars shared between A and C, the stars sort of in the middle of this Venn diagram, those two fields, their calibrations should agree on how bright those stars are. Let's assume that they're not variable stars or anything. So I'm going to compute a calibration for C, which minimizes the residuals between what exposure A thinks is the calibration for those stars and what exposure C thinks is the magnitude of those stars. And so that sets me up with a good calibration for exposure C, and then I can essentially repeat the same game between exposure C and exposure B. And so now the stars on the right are going to link my calibrations between these two fields, even though neither of them has any calibration stars directly in them. And so this concept actually it's not just something that you have to do sort of one-to-one and like go, okay, this field to that field to this field to that field. All of these, this is all basically just a linear least squares minimization problem every time I compare these two fields. And so I can actually do the comparison of all the fields in my survey, as long as they all have some overlap with other fields. I can solve that entire system of calibrations all at one time. This system of linear least squares essentially turns into sort of tens of thousands and hundreds of thousands of equations, because you have an equation for every single star that you need to have a consistent magnitude between all the different exposures that it falls on. But that's something that software is very good at. This is a sparse matrix least squares minimization problem, and computers are good at this sort of thing. And so this has been sort of a standard technique for about the past 10, 15 years for calibrating, or at least developing an internal calibration for all of the images in a large survey, and putting all of those fields on sort of the same photometric basis. And so maybe we should step back a little bit and think about what this is. What are the challenges that we're trying to overcome with this method? And one is just that we know that the stars are the same brightness, or at least the ones that we choose to calibrate against. But we're essentially solving for the fact that the transmission through the atmosphere and through the telescope and into the CCD tends to vary within a night and from night to night. At the very least, the atmosphere creates this variation just because as objects are in different parts of the sky at different times in the night, you're looking through more or less air, and that air extincts some of the light, and so images that are taken sort of low on the horizon will have fewer counts in their stars in your measurement of those stars than if you had taken that exposure at sort of towards zenith. And so sort of the traditional technique before having all these sort of large sky surveys was to model effects of something like air mass or other variations in the telescope throughput by sort of measuring them specifically, but by doing the sort of large-scale calibration for the entire survey, we can essentially get the same information for free without having to model some of those details. So the end result is that we can treat these large surveys as a consistent photometric system, which doesn't mean that they are absolutely perfect. They're not like the definition of what a magnitude is, but at least gives us high confidence that a star in pan-stars in G-band in one direction is going to be the same brightness as a star of the same magnitude in G-band in another part of the sky. Pan-stars has sort of linked those two together with its survey. This simultaneous solving method has been done for basically all the large surveys, and so I've listed the different papers here that did those calibrations because they're really fascinating to read, because it's a really cool physics problem and a really cool computational problem at the same time. So I think it's a fun read. Okay, short break. So the second question I posed was, is 0 point all that matters? And we've, the assumption that the 0 point is the only calibration term is essentially assuming that all of the calibration is what we call a gray calibration. It has no spectral dependence. It's only sort of scaling up and down the total level of flux coming through the system without affecting red photons or blue photons preferentially. And the real challenge for surveys today is that we've sort of learned that there's spectral dependence basically all throughout the system. There's all sorts of ways to introduce biases between reddish objects and bluish objects. And in order to do accurate photometry, we need to understand those effects and be able to calibrate them out. So I'm going to kind of illustrate cartoonishly what those color effects do to us. So you could say, well, Pan-Stars has a G-band filter, and I can go buy a G-band filter and put it in my telescope, and aren't we measuring the same thing? Like, it should all be fine. Like, my G-band should be just as good as Pan-Stars G-band. But in detail, it's a little more complicated, because chances are that G-band filter might not be exactly the same one. It's the same. It might not have the exact same transmission that the one that Pan-Stars used. There also might be other sort of transmission effects in your telescope or in the Pan-Stars telescope that kind of changes the shape of that filter a little bit. And so to just illustrate that in the cartoon, I'm going to just say that my filter, which I think is the same as the other survey, is actually sampling a little bit bluer spectrum of the object than the original that I'm trying to match. And so it's shifted in wavelength a little bit. And for an object with a flat spectrum, that's fine. The other survey measured 1.0 Janskis, or whatever flux unit you like. My survey, I measure 1.0. That's fine. Good. I can do science with this filter. But if I have a blue source that I'm measuring, because it's blue, and because my filter is shifted to kind of preferentially detect that blue flux, I'm going to see that object as being a little bit brighter than the other survey would have. So I'm going to say, oh, that's a 1.1 nanojansky or whatever source. And in kind of the opposite direction, if there's a red source in the image, I'm going to detect a little less flux than the other survey would have, because my filter is not quite so sensitive to that. So I'm going to say it's a 0.9 nanojanskis. And that's challenging, because there's nothing I can do to the 0 point that will correct for both the blue stars in my image and the red stars in the image at the same time. So at the very least, I'm adding noise. I'm just sort of scattering these magnitudes around for no reason other than my filter's a little bit different. But it might be a little bit worse than that because it's a systematic effect that depends on the color of the source. And so you could imagine, say, if I'm trying to measure high redshift objects, and my higher redshift objects are slightly redder, and so they have slightly fainter magnitudes, I might come to different conclusions than if I had actually carefully calibrated my magnitudes to match the other survey. So the kind of traditional solution here is to adopt what we call a color term. So now my magnitude equation is, I've added, it's the basic same thing of counts plus the 0 point, plus I've added this C coefficient times a color. So now for each star, for each galaxy, I need to know a G minus R color, and I can't know that from just one image, so I got to bring some other information to bear to know how to correct each individual object. But when I know that color from the different bands, I can sort of estimate how much my photometry differs from the original survey that I'm trying to compare to. So I measure this constant C, and then I use that to correct for these different color variations in the objects that I'm measuring. So this sort of variation in the edges is it's a understood problem, and you can find published tables that list all of the different estimates of the color terms if you want to go from Sloan to pan stars, or from pan stars to decam. These are pretty well measured. They work best if you're looking at sort of main sequence stars with sort of well-behaved spectra. If you're trying to also apply it to some very weird spectra, then it's a little bit more challenging. But it's to do really high precision photometry, it turns out that there's more complications than just sort of making the filters match each other. And it turns out that the total throughput through the entire system, including the atmosphere, is really time dependent. And so even within a single survey, even within LSST, there's going to be variations in this in the spectral dependence of the throughputs from night to night, and even sort of within a night we expect this variation. And I think the atmosphere is sort of the best example of this, where I've shown on the left, this is a picture of the dark energy survey passbands, where it includes the effects of the atmosphere. So that's why you see it kind of tapering off strongly on both sides, but it also is why you see these sort of deep, they look like spectral lines because they're atmospheric spectral lines that are absorbing some of the light, in the middle of the filters, and sort of on the right edge of the Z-band filter, you see how it gets extincted a whole lot. And on the right side, I've shown a model atmosphere, where this is separated out the different components of absorption. So this big feature in Z-band is caused by water vapor in the atmosphere. But you can see that there's other components that are also causing these spikes. So some of this is caused by oxygen, and this big kind of gradual roll-off on the blue side is caused by scattering, Rayleigh scattering or aerosol scattering, where it's actually sort of kicking light out of the path to the telescope in sort of a broadband fashion. And this would be a little bit more tolerable if it was all fixed, but all of these components are actually varying in their relative intensities because basically of weather. Like the weather is changing the amount of water vapor in the atmosphere, it's changing the aerosol content of the atmosphere. And so that's going to make the telescope, which has the same hardware, the same filters, the same sensors, have slightly different dependence on the colors of the sources because of this weather-based variation. And so the Dark Energy Survey has gone into doing a lot of work to try and model that weather variation from the photometric data itself, which is super cool, and it's described in this paper here, if you're interested in more details. But a lot of my goal here is to sort of look forward to sort of what the plan is for the Rubin Observatory. And if you've seen pictures of the construction site, you might notice that there's this other dome sort of off on another hill adjacent to the observatory building under construction. And that houses what we call the auxiliary telescope. And the auxiliary telescope's goal is to continuously, throughout the night, take spectra of standard stars with just really broad wavelength coverage in order to give us in order to tell us what the atmosphere is doing through the course of a night and night to night. So here's actually an image off of the telescope. And you can see that it's a slitless spectrograph, so it's just going to take all the stars in the field of view, and it's going to produce a spectrum. It's going to produce 2 spectra, actually, for every single bright star. And you see for this bright star here, there's a bright band on top and a bright band on the bottom, which actually is a spectrum. And so here's one of those spectra where it's been modeled, and you can see the lines point to where the different atmospheric components can be measured. And so this gives us a way to measure the water vapor along the line of sight to one point in the sky relative to the amount of oxygen absorption to that same point in the sky. And so with this set of measurements for the entire survey, this gives us another way to sort of make sure we can calibrate our passbands or standardize our passbands and know that they're measuring the same thing from night to night to night, and not just being suffering from atmospheric variations. So I've said a lot of things. I'm just going to sort of summarize the main points here. One is that large surveys basically self-calibrate to create their own internally consistent photometric system that's separately is tied to an external system to calibrate the physical flux based on a small number of calibrators, but that's mostly sort of like a separate operation than the internal self-calibration of the survey. Magnitudes are always dependent on the bandpass, and not just like from 500 nanometers to 600 nanometers, but the exact shape of that transmission through the entire system, including the sensor, including the filter, including the telescope, including the atmosphere. This effective bandpass changes between surveys, and also changes within a night due to atmospheric effects, among other effects. And that's really sort of what's driving the forefront of photometric calibration, is trying to standardize the band passes and calibrate out these variations in order to get really precise and accurate photometry for the objects in the survey. That's it.